Imagine tuning the cruise control on a car. If the controller gain, which engineers call K, is too low, the car takes forever to reach the speed limit. If you crank the gain too high, the engine overcompensates, jerking the car forward and potentially spinning out of control. To design a safe system, you need to find the exact sweet spot for that gain. But recalculating the closed-loop system dynamics for every possible turn of the dial is incredibly time-consuming, especially for higher-order systems. That is where the root locus comes in. It provides a single graphical map that plots the exact path your system's closed-loop poles will travel as the gain increases from 0 to infinity. Take a look at this block diagram. We are going to deconstruct the specific transfer function shown here. G of s equals s plus 6 over s plus 2 times s plus 4 times s plus 9. By translating this single equation into a continuous map, we can pinpoint exactly how the physical system will behave before a single line of code is written or a single motor is turned on. The construction of a root locus follows strict rules. The first rule establishes our starting and ending points. The paths always originate at the open loop poles when the gain is 0, and they terminate at the open loop zeros as the gain approaches infinity. Looking at our transfer function, the numerator gives us a 0 at -6. The denominator gives us 3 poles at -2, -4, and -9. We plot these on the complex S-plane, marking the poles with an X and the 0 with an O. Next, we need to know which parts of the real axis actually contain a valid path. We find this using the odd number rule. Scanning from right to left across the axis, a segment is part of the locus only if the total number of poles and zeros to its right is an odd number. This graph highlights the results of that sweep. The bold lines show that the system can operate on the real axis strictly between -2 and -4, and from -6 stretching left toward -9. But we have a mathematical imbalance. There are 3 starting poles, but only 1 ending 0. That means the 2 remaining paths must travel outward toward infinity. They follow predictable escape routes called asymptotes, anchored at a calculated centroid of -4.5, shooting out at 90 and 270-degree angles. We now have the basic skeleton of the system and its escape routes. The next step is to locate the exact coordinates where the internal pressures force these paths to leave the real axis. Look at the valid segment between -2 and -4. As gain increases, the poles originating from those 2 points move directly toward each other. They inevitably collide and break away into the complex plane. To find the precise coordinates of this collision, we evaluate the closed-loop characteristic equation. We rearrange the formula to isolate the gain, K, and then take the derivative with respect to S, setting it to 0. Applying the quotient rule generates a complex polynomial. Solving the numerator yields 3 mathematical roots, one at -3.08 and 2 complex roots near -6.7. Only one of these mathematical outputs represents the physical reality of our controller. By overlaying these 3 points back onto our wheel axis map, the true breakaway point becomes obvious. The value -3.08 is the only solution that sits squarely on the valid operating segment between our starting poles at -2 and -4. The complex roots are discarded. This final diagram combines our poles, segments, and asymptotes with that precise breakaway point. You can clearly see the red and green branches breaking off the real axis at -3.08 and bending outward along their asymptote highways. This curve is a strict boundary map. It defines exactly where the system's dynamics are allowed to exist at any possible gain level. With the map drawn, we can now use it to make engineering decisions. Watch what happens as we turn the gain dial up from 0, driving the system's poles along these designated paths. First, we check for stability. Because all the branches remain entirely on the left half of the S-plane, the system is inherently stable at any gain. It will not spin out of control. Next, we look at the type of response. While the poles travel along the real axis, the system behaves smoothly without oscillating. But the moment they break away into the complex plane, the physical system begins to oscillate. And as those curved paths bend closer toward the vertical imaginary axis, the system's damping decreases, causing higher overshoots in the physical hardware. Every feature on the graph translates directly to physical behavior. Real axis locations dictate non-oscillatory responses. Complex coordinates predict oscillation, and the strict left side boundary guarantees stability. By mapping out the root locus, engineers avoid the danger of trial and error tuning. They lock in the speed, stability, and safety of a system entirely through geometry.